Hello everybody, welcome to an episode of Science Time with Terry. Today we are going to be overviewing a recent debate I did with CYB, otherwise known as Challenge Your Beliefs, and the debate was primarily over the Big Bang, T equals 0, and a couple of other topics that we covered. And I wanted to just start making a video series about each topic just to cover it in a more in-depth and straightforward manner to really cut through the indirectness and false arguments and such that were found in the debate. I hope you think critically about these evidences and arguments, and without further ado, let's get into the video.
We ask your help in this fateful moment as sign that we scientists do not stand alone.
I agree.
We passed the 6-minute mark in our countdown for Apollo 11. The flight to land of the first men on the moon. We're on time at the present.
And I put in it one living cell.
Over time, you will come closer together, ultimately bumping into each other at the North Pole.
So journey with me to the sun.
Of sandstone, shale, limestone that goes continent wide. There are 4 other big sequence packages of strata.
Let us go faster. Bear with me. What is time?
You're trying to use a set of mathematics which is known to be incorrect at those small scales, and say that there's nothing before, nothing after. That these are things that are predicted by that. But then when you go and say, okay, well let's do that, let's follow that, you do get the Hawking Penrose singularity theorem is the white hole in a Penrose diagram. It's the point at which all world lines converge, and what's on the other side, world lines come back out of there in exactly the same way as if it's infalling matter from another universe into a black hole, singularity.
You're equivocating that to their description of the singularity at the beginning of the universe, in which they do not have an Einstein-Rosen bridge in the middle that is going to a white hole. That's the whole point, is that I agree that you're right, that for black holes, the Hawking Penrose diagram and theory does predict what you just described. But it doesn't predict the same thing for the beginning of the universe, mainly because our universe is expanding. And that was the biggest reason why they had to deal with it differently, is because a black hole is not in the same state of expansion as the universe as we know it. And so you have to account for that in your equations. And basically, like, the whole point that, again, I forgive me if it's a bad way of saying it, but it seems like you're trying to avoid it, is that, like, we can agree, if you want, that whatever general relativity predicts for black holes and, any singularity of any kind is wrong because we know it breaks down at that scale. Fine, I'm all in your camp. We're 100% in agreement. But that means that we need to abandon the Big Bang model that is accepted by currently the consensus of scientists, because it predicts the same thing based on those Penrose diagrams. Like, we may know that those Penrose diagrams are wrong, but that is what the model predicts. And so
you're going to learn some things as you do your degree about this sort of way of looking at the world, that you have a lot to learn yet. I'm sorry, but this is it's just wrong. That's not how science works.
Alrighty, you claim that's not how science works. Let's do a little learning on Penrose diagrams, shall we?
We need a space-time diagram of a black hole. On the left is the singularity at r equals 0. The dotted line at r equals 2m is the event horizon. Since the black hole doesn't move, these lines go straight up in time. Now let's see how ingoing and outgoing light rays travel in this curved geometry. When you're really far away, the future light cones are at the usual 45 degrees. But as you get closer to the horizon, the light cones get narrower and narrower, until right at the event horizon, they're so narrow that they point straight up. And inside the horizon, the light cones tip to the left. But something strange happens with ingoing light rays.
They fall in, but they don't get to r equals 2m. They actually asymptote to that value as time goes to infinity. But they don't end at infinity, right? Mathematically, they are connected and come back in, and they're traveling in this direction. And this bothered a lot of people. This bothered people like Einstein because he looked at these equations and went, well, if nothing can cross this sort of boundary, then how could there be black holes? How could black holes even form?
So what is going on here? Well, what's important to recognize is that this diagram is a projection. It's basically a 2D map of four-dimensional curved space-time.
It's just like projecting the 3D Earth onto a 2D map. When you do that, you always get distortions. There is no perfectly accurate way to map the Earth onto a 2D surface, but different maps can be useful for different purposes. For example, if you want to keep angles and shapes the same, like if you're sailing across the ocean and you need to find your bearings, you can use the Mercator projection. That's the one Google Maps uses. A downside is that it misrepresents sizes. Africa and Greenland look about the same size, but Africa is actually around 14 times larger. The Gall-Peters projection keeps relative sizes accurate, but as a result, angles and shapes are distorted.
In a similar way, we can make different projections of 4D spacetime to study different properties of it. Physical reality doesn't change, but the way the map describes it does.
He had chosen to put a particular coordinate system over space and have a time coordinate, and off you go. It's the most sensible thing to do, right?
People realize that if you choose a different coordinate system by doing a coordinate substitution, then the singularity at the event horizon disappears.
It goes away, that problem goes away, and things can actually cross into the black hole.
What this tells us is that there is no real physical singularity at the event horizon. It just resulted from a poor choice of coordinate system. Another way to visualize what's going on is by describing space as flowing in towards the black hole, like a waterfall. As you get closer, space starts flowing in faster and faster. Photons emitted by the spaceship have to swim against this flow, and this becomes harder and harder the closer you get. Photons emitted just outside the horizon can barely make it out, but it takes longer and longer. At the horizon, space falls in as fast as the photons are swimming. So if the horizon had a finite width, then photons would get stuck here. Photons from everything that ever fell in. But the horizon is infinitely thin, so in reality, photons either eventually escape or fall in. Inside the horizon, space falls faster than the speed of light, and so everything falls into the singularity. So Oppenheimer was right. Someone outside a black hole can never see anything enter, because the last photons they can see will always be from just outside the horizon. But if you yourself go, you will fall right across the event horizon and into the singularity. If you take this map and transform it so that incoming and outgoing light rays all travel at 45 degrees like we're used to, then something fascinating happens. The black hole singularity on the left transforms into a curved line at the top. And since the future always points up in this map, it tells us that the singularity is not actually a place in space, instead it's a moment in time. The very last moment in time for anything that enters a black hole.
Imagine that.
The map we've just created is a Kruskal-Zeker's diagram. But this only represents a portion of the universe, the part inside the black hole's event horizon and the part of the universe closest to it. But what we can do is contract the whole universe, the infinite past, infinite distance, and infinite future, and morph it into a single map. It's like using the universe's best fisheye lens. That gives us this Penrose diagram. Again, light rays still always go at 45 degrees, so the future always points up. The infinite past is in the bottom of the diagram, the infinite future at the top, and the sides on the right are infinitely far away. The black hole singularity is now a straight line at the top, a final moment in time.
So it's pretty clear that if you understand anything about Penrose diagrams, that this line at the top of the graph represents the end of time, basically t equals 0. So if you want to claim that the t equals 0 at the beginning of the universe, singularity, doesn't make sense, then you have to also admit that this also does not make sense.
We know there's a problem at that point. The Penrose diagrams, the general relativity do a great job of describing almost everything except where things get really squidgy in the middle there. And we know that's all fine, and it gives us great tools to work with for almost everything. But trying to squeeze it all in to try and make it sound like there's more there, it just isn't.
I mean, I think my objection to what you're saying, Terry, is that you're saying that because t equals 0 is wrong, and we know it's wrong in the Big Bang, that we are saying that the Big Bang theory is wrong. We're saying that the Big Bang theory is right as much as it's verified, but at t equals 0, it just doesn't apply.
And what I'm trying to get you to see is that the Big Bang model, as accepted by the consensus of physicists and cosmologists, does indeed describe t equals 0 as the beginning point of the universe. Whether it's 100% fully understood or not, that's way up for debate because we can't probe it yet. But
I think that's the trivia point.
And I would say that you're assuming something about the consensus of physics that you're wrong about.
I mean, you say that, but it's not something I'm wrong about.
Really, I'm assuming something about the consensus of physics that I don't know anything about or that I'm wrong about.
The beginning of everything, the Big Bang. The idea that the universe was suddenly born and is not infinite. Up to the middle of the 20th century, most scientists thought of the universe as infinite and ageless. Until Einstein's theory of relativity gave us a better understanding of gravity, and Edwin Hubble discovered that galaxies are moving apart from one another in a way that fits previous predictions. In 1964, by accident, cosmic background radiation was discovered, a relic of the early universe, which together with other observational evidence made the Big Bang the accepted theory in science.
One of the most noticeable features of time is that it has a direction, right? That there's a difference between the past and future. Sometimes we think about this as just an intrinsic feature of reality, like the past already happened, it's in the books, the future is up for grabs, it hasn't happened yet, and the present is where we live. But then along comes physics, and what people notice about our best theories of physics is that those theories do not distinguish between the past and the future. But in our everyday lives, nothing is more obvious. It really requires a bit of mental discipline to say, well, time could exist without an arrow. And one way of thinking about that is, there is no intrinsic arrow of space, but there's still space, okay? We live in a three-dimensional world, up, down, left, right, forward, backward. At the level of the fundamental laws of physics, there's no special direction in space. And how you perceive that is, imagine you're an astronaut. You're flying around in your little spacesuit. There wouldn't be any difference between any direction you could look. There's no experiment you could do in physics that would point out a direction in the universe, but space still exists. Likewise, time would still exist even if there wasn't an arrow. But here on Earth, we do have an arrow of space. If I pick up a coffee cup and let it go, it will always fall down. There's clearly a distinction between up and down. No one is tempted to think that's a fundamental feature of the universe. It's not because downness is embedded in the laws of physics. It's because we live in the vicinity of an influential object, the Earth. The arrow of time is exactly the same way. We, in our everyday lives, perceive an arrow of time because we live in the aftermath of an influential event, the Big Bang. And that gets us into a realm of the concept of entropy. Entropy is how messy, how disorganized, how random a system is. When things are nice and neat and tidy, they are low entropy. When they're all messy and all over the place, they are high entropy. And there's a natural tendency of things in the universe to go from low entropy to high entropy. This is called the second law of thermodynamics. The real question is, why was the world ever low entropy to begin with? Why was the world lower entropy yesterday than it is today? The explanation is not completely satisfying, to be honest. The explanation is the following: because it was even lower entropy the day before yesterday. And why was the universe even lower entropy the day before yesterday? Because it was even lower entropy the day before that. And this chain of reasoning goes back 14 billion years to the Big Bang, to the origin of our observable universe in a hot, dense state, a very low entropy state, and the universe has been increasing in entropy ever since. And this is called the past hypothesis by philosophers. David Albert, who's a philosopher of physics, gave it this name. So now we say, if you know that the world is made of atoms, and you know what entropy is in terms of rearranging all those atoms, and you know the past hypothesis, that the entropy of the universe started really low, then you can explain everything that happened after that.
Interesting, this idea of the Big Bang created the universe. That's what Einstein's theory says. That's textbook cosmology, if you like. But the current textbook picture is there was a phase in the universe's life before the Big Bang, if you define the Big Bang as the hot, dense phase from which the universe appeared to sort of burst forth 13.8 billion years ago. And that phase is called inflation. So what we think happened is that before that, the universe was accelerating exponentially fast. It means it was doubling and doubling and doubling in size. And the numbers are ridiculous. We think that if you started with a universe that was smaller than a single atom, then it would be bigger by a long way than the whole observable universe, 350 billion galaxies in it, in less than a millionths of a second. So a very rapid, exponentially fast expansion. And when that stopped, all the energy that was driving that expansion got dumped into space. It heated it up. It produced the particles of matter out of which we're made and all the things that we see out there in the sky. And that's what we see as the Big Bang. So that sounds fanciful, but that's standard cosmology at the moment. The big question then is, well, what started the inflation? What stopped the inflation? How long did the inflation go on for? And the answer to that is, we're not sure. We don't know.
What is time? A deceptively simple question, yet it is the key to understanding relativity. It is also the reason my hair is going grey. When we describe motion, we do so as a function of time. 10 meters per second, 100 miles per hour. But the mathematical description of velocity is moot, unless we can define time. Is time universal? In other words, is there an audible tick-tock throughout the galaxy? A master clock, so to speak, forging ahead like Mozart's metronome? The answer, my friends, is no. Time is not absolute. In fact, for us believing physicists, the distinction between the past, present, and future is but a stubborn illusion. A lot to consider, I know. I know. But understanding time is essential to understanding relativity. Now, I want you all to close your eyes. Not to worry, I don't bite. But I am on the lookout for a new pen. Go on. Close your eyes. To truly grasp the idea of time, we must take a step back and ask, what is light? So journey with me to the sun.
So obviously make up your own mind about the evidence I presented here, but it's pretty clear to me that the consensus at the moment is that the Big Bang does indeed basically say that time came into existence at t equals 0. So if you want to say that t equals 0 is wrong, then that's fine, but that means that the Big Bang model itself is wrong. And that's why Roger Penrose and Hawking came up with a new theory, and that's why there's plenty of other theories that are trying to take into account quantum gravity. We'll get into more in depth into that next episode, but for now I think I'll just leave it there. I feel like this is kind of beating a dead horse on this point, so if you want further reading on this from official PhD holders and physicists and cosmologists like Stephen Hawking, Sean Carroll, and the likes of people like that, then I will leave a couple links in the description. You can look at those yourself and come to your own conclusions. Let me know what you think in the comments, and leave a like and subscribe. Thanks for watching this episode of Science Time with Terry.
It's as though there was a force pushing you together. DNA contains a similar number of genes that directly code for proteins as a lot of simpler life forms do.
No one has measured the speed of light. That's ridiculous.
World and other continents in that general style.
Faster. Faster.
The real reason for you coming together was that you were both on straight paths, geodesics, on a curved surface.
What is time?